Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics over in Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how things evolve, how things interact, all of the cool stuff happening inside the universe. I love being a scientist. I love getting to study the universe. It's a really, really fun job. I love that I'm paid to do this. And I really like chatting to everybody about all of the really fun stuff that I get to work on. So the idea of the stream is this is interactive. You people can ask me anything you want, and I will do my best to try to answer. As always, I do not have all the answers, but I will try my best. And I see we have some of the regulars joining already in the comments. And Shamita, Scott, David, great to see everybody as always. If you're a first-time viewer, welcome. I hope you like it. If you haven't done so already, please do subscribe, like, leave a comment, all the usual YouTube stuff. It really does help promote my video to other people, which is nice because then I get random people finding my stream. So do all the usual YouTube stuff, you know, the buttons to press, make stuff happen, press button, see what it does. Great to have everybody here as always. So I don't have a specific topic planned this week. That I've been I was on holiday. It was a really, really nice holiday. I had a great break. Hey, Paul. Hey, Pratt. Great to see you all. As always, very nice to see everyone. So I had like a 10-day break from work. It was really nice. I managed to relax like 2 days. And then I was running around doing stuff. And I was on a trip in Stockholm, which was really fun. I walked about 70 kilometers in the span of 5-6 days. It was exhausting, which is why there was no stream last Sunday, because I got back home Sunday afternoon and I crashed on the sofa and did not move. So back this week, but that also means this week I've been kind of catching up with work and getting back into the flow of things, so I didn't have time to prepare a special topic, which means today is the day where I get to ramble about anything that I find specifically interesting, and you all get to ask me questions to direct the conversation in whichever direction you want. As always, you can ask me about anything you want: science, academia, physics, particles in the universe, why particles don't have a conscience, anything you want, you can throw it my way, and I will do my best to try to answer the questions. And I was also just very thrown off at the start because I have my nice loading screen, and I'm pretty sure either the font or the layout of my loading screen has changed, which is very bizarre because I didn't change it. So that's very weird. Anyway, that's a minor thing, typographic thing. I just noticed that the font and the layout has changed. So now I'm going to have to go back and check my old streams and check the new ones and figure out why something has changed in my loading screen. Because both Restream changed, I updated my laptop. There's a lot of things that have changed, but it looks different, and I don't like things looking different. Scott, yes, I did get your notification about the to-scale solar system spread out all through Sweden. It's very cool. I got to see, so there is this in Stockholm, and well, starting in Stockholm and spreading out to the rest of the Sweden, there is a to-scale solar system model, which is pretty cool. There's a massive building in Stockholm that is like the biggest round building in Europe, I think, and that serves as the sun. So I got to see the sun, and I accidentally bumped into Mercury at some point. I wasn't looking for it, but I was in a place like, oh, hey, look, there's Mercury. So I got to see those two. Then I didn't go and find the rest because it's quite big and takes quite a while to find everything. Hey, David Dunn, great to see you as well. I see lots of comments already coming in. Yeah, so the Indian Space Agency did indeed launch a mission to the moon, which is very, very cool. We need more moon missions. We need more stuff going to the moon. So that was very cool. And I think the launch was very, very successful. No issues. So that's very cool that we're getting another thing going to the moon. It's always fun. Okay. Hey, James, didn't say hello to you. Great to see you there as well. FYI, there is one of those to-scale solar system. There is one of those to-scale solar systems in Washington, D.C., starting at the Air and Space Museum. That is very cool. I haven't actually been to Washington. So if I'm ever there, I'll also look out for that one as well. And as always, I'm talking quickly and not catching my breath. So need to slow down, and then I'll read Paul's comments and go from there. Okay, if universe had a long, almost steady state period before recent accelerated expansion, does that make using redshift to measure distance very unreliable because most of the time it wasn't stretching? That is a very good question, Paul. The thing is, we have not actually reached one of those steady state situations. So let me just bring up everyone's favorite picture of the universe. And I don't mean the CMB, I mean this one. No, let's go for the other one, that's nicer. Okay, this one here. So we had this initial period of exponential expansion, which is inflation, And we have the accelerated expansion today. Now, in between these two times, the universe was still expanding. This expansion didn't stop at any point, it was still ongoing. So, the initial expansion, we have the Big Bang, or this moment of exponential expansion in the very early universe, things start growing from there. And then it takes quite a while for things to gradually slow down. Now, what we thought was going to happen is things would gradually slow down and eventually collapse back upon itself. And at some point, you would reach this kind of steady state where you're neither expanding nor contracting. However, a couple billion years after the end of inflation, dark energy took over the universe. We entered the dark energy dominated era, which is the one we live in today. And dark energy is driving the accelerated expansion once again. So the universe is expanding, this expansion is accelerating. So the universe is expanding faster and faster today than it was in the past, or at a quicker rate today than what it was in the past. But there wasn't actually a steady state solution at any point. So at no point did the expansion reach the stage where it slowed down enough to not be considered. So, you know, in this diagram that I have here, it almost looks like it goes flat in the middle, but you can see it's still stretching out slightly. And in other visualizations, like this one here, you can see it never does actually go completely parallel. So at no point is it neither expanding nor contracting. So there has always been ongoing expansion. So then going back to Paul's question here, the question was, how reliable is it to use redshift to measure distance because of the differences in stretching, or if it wasn't stretching at some point? So redshift is a measure of how much light has been shifted as it travels through the universe. We know that because of the expansion of space-time, everything is moving away from us. The fact that everything is moving away from us means that light is traveling away from us. If you consider an ambulance, when an ambulance, with the big siren going off, when an ambulance is coming towards you, it sounds different than when it's going away from you. You can also see this if you're in the ocean, if you're trying to swim against the current or following the current, right? It's the different swishing movements there. So in the universe, you have something similar. Every particle of light, every photon, has an associated wavelength, which you can imagine can be depicted kind of like this. Of course, Slinky Toy had to come up. So as the galaxies, for an example, are moving away from us, the photons they emitted are traveling through the universe, and their wavelengths gradually get stretched and stretched and stretched because it's dragging behind as the universe is expanding. This leads to redshifting. It's shifting towards the red end of the electromagnetic spectrum. Now, even if hypothetically, so we can use this to measure distances because based on how much light is stretched, we can figure out how far it's traveled. So Paul's question here is a very good question of if the universe stops expanding, does this suddenly stop? Now, the thing is, the galaxies in the universe are moving all away from each other. So then there's a question of if the universe stops expanding, do galaxies kind of immediately feel this? Do they stop immediately? Are they moving by themselves, or are they only moving because of the expansion of space-time? I mean, it's a bit unclear how you define this. But we think redshift is a rather reliable measure of distance, at least up to some point. Then it does get a bit trickier. The further you go out, then it gets a bit trickier. But redshift is a very good indicator of the distance of objects. So even if we had entered a steady state where the universe is neither expanding nor contracting, we can still use redshift to a pretty good degree to measure distances of objects. But we know that the universe never entered this period. It never actually reached a point of stopping and slowing down enough where this would be a problem. The universe was expanding a lot in its infancy because of inflation. Universe is expanding a lot today because of dark energy, or we think dark energy. We haven't actually figured out what's causing it, but dark energy seems to be the most likely solution. Okay. I just missed some comments, so let me get back to these comments. Your friend told you about the one in Washington, but the Stockholm one is much bigger, I guess. I'm not sure about the scaled solar systems. I've seen parts of the Stockholm one. If I'm in Washington, I'll check it out. I think those things are pretty cool to visualize stuff, but also you kind of lose a sense of the scale if you need to walk to the next thing and then it's like, okay, here's another sphere. Now let me walk 3 days and find another sphere. I'm not sure if that helps people get a sense of scale or not, because to me, then I lose track, right? I'm not going to remember something I saw 3 days ago. It's like, oh yeah, here's another sphere, cool. But I get that it's a cute thing for some people. Was dark energy the cause of inflation, or is that not a question that can be answered given inflation wiped out any continuity with what went before? That is an excellent question, David, and that is a really nice way of phrasing that question. So, losing my voice already today. This is going to be fun. So we don't exactly know what caused inflation, this period of exponential expansion when the universe was very, very, very young. Let me just bring up my thingy again, and let's not actually turn myself off in the process. So we have this period of inflation in the early universe, but we know that inflation deleted the memory of everything that came before. But we have some ideas as to what might have caused inflation. Usually we call this an inflaton field because we're great at naming things. A field is something that has a value everywhere in space. So for an example, if you're talking about the temperature of the room, this is actually a field because at every point you measure, you get a different value. Whereas if you talk about the speed with which something is falling down a hill, this is one number because it's going to change, but it's one number. It doesn't matter where you make the measurement in the room, for an example. But the universe is full of fields like the electromagnetic field. There could have been a field in the early universe, which we call the inflaton field, which is the field that has a lot of energy and causes this inflation. We call it the inflaton field because it causes inflation, and we're very, very, very good at naming things. However, this is like, what is the inflaton field? We don't know. What caused the inflaton field to inflate and to then stop inflating? We don't know. We're still trying to figure these things out. But a lot of people think it's not the same thing as dark energy. So we know that inflation took place in the very early universe, and dark energy is dominating today. So yes, I just noticed the comments about the shape of this figure again. Not going to go there, not going to make the joke again. So the thing is, inflation happened at very, 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 very high energies, whereas dark energy is later in the history of the universe, so the energy scale is a bit different. So additionally, there was this period in between where there was no inflation happening, no exponential expansion. So then it's the question of what could have caused the inflaton field or dark energy, if you want to say they're the same thing. Like, why would it happen and then stop happening and then happen again? So another reason we don't think dark energy caused inflation is the way dark energy dilutes with the size of the universe. So as the universe grows, dark energy spreads out, matter spreads out, radiation spreads out, and they all spread out in a different way. This is something that is really fun to calculate, and they have different, mathematically speaking, they have different dependencies on the scale factor, which just means they spread out in different ways. Radiation spreads out faster than dark matter, than dark energy. And this is why in the very early universe, you have a lot of radiation, but then it dilutes away quicker. And then you get a lot of matter, and then you get dark energy. So the dark energy that dominates the universe today, that is driving the accelerated expansion, would not have been the dominant contribution in the early universe at the time of inflation. So we don't think dark energy is the cause for inflation. Then you can turn it around and say, okay, but could it be the other way, that whatever caused inflation is the same thing that caused dark energy? There are some people working on this, but it's quite hard to connect the two, mainly because of the different energies at which they take place and the different states of the universe or time frames at which they take place. So we're pretty sure inflation happened. We haven't been able to prove that yet, but we're pretty sure inflation happened. Of course, you never actually prove a theory, you just find a lot of evidence for it. We're pretty sure inflation happened. We're still trying to figure out the details, what caused it and all that stuff. Incidentally, gravitational waves might help us understand that, which is really cool because gravitational waves are amazing. We're still trying to figure out what dark energy is. It's unlikely that gravitational waves will help much with dark energy, but we're still trying to figure out what dark energy is. And there are some people working on this question of, are they connected? But generally, it seems like the answer is no. It doesn't look like we found a solid mechanism to connect them all. Let me just check if there were comments to that. Okay, going back through the questions, as always, if I miss a question, I will try to catch up with it. Feel free to ask follow-ups or clarifications. If anything I say is not clear, that's on me. Please ask me to re-explain it. You know, I get people sometimes say, like, you sounded like you knew what you were saying, but I didn't understand it. If you don't understand what I'm saying, that's on me for not explaining it properly. So please do ask. The point of these streams is that everyone should understand what I'm saying. If you don't, please do ask, and we'll go through things again. I'd much rather spend the whole stream talking about one topic, then have people leaving saying I didn't get a single word. So please do ask if you have questions, as always, and remember there are no stupid questions. Okay, so we did the dark energy inflation. Great question. Question from James. Since this is the anniversary of first atomic bomb test, is there any science that is under research discussion that can be devastating to humans? Yeah, that's always a difficult question, isn't it? Because, yeah, it's a difficult question because I'm not like trying to hide some super scientific, super secret research that is ongoing. But often scientists come up with inventions or discoveries without thinking of the possible consequences or the way that humans will then go, I wonder how I can turn this into a weapon, or I wonder how we can turn this into something profitable. Because, of course, anything you discover or invent needs to be profitable because capitalism. But there are not, to my knowledge, scientists working with the objective of creating the next nuclear bomb. There are people trying to do cool stuff with science, and there are these consequences. Of course, that is not always true. And I think more than something like a quantum gun or nuclear fusions and nuclear bombs, a big concern we have going forward is bioweapons. And that's something that people are working on, unfortunately. That's something that is way, way, way out of my field of expertise. So I'm going to leave it at that. But there was a very good quiz very recently on the topic. So Quiz Gazette is a science outreach channel. It's where I got this map from and a few other merchandise that you'll see lying around. And they had a video about that. But in general, I would say that don't worry about scientists inventing the next nuclear bomb. You know, we have bigger issues as in climate change, which is the biggest threat that has ever faced humanity. And if we don't fix climate crisis soon, we won't be around having this conversation in 50 years. But yes, not to my knowledge, there are not scientists working on things like quantum guns or the next nuclear weapon, other than bioweapons and stuff like that. But yes, let's move on from that very depressing topic. The sound you hear when an ambulance coming is the sound of your money leaving in America. Yes, well, America needs a good healthcare system. Most countries need a better healthcare system, but especially America. And I'm not going to do that rant. I'm mad with it. Okay, I saw that one, not reading that one out loud. If the universe was contracting, would wavelengths become more condensed then? Yes. So it's quite cool. If the universe was contracting, you'd see everything rushing towards you, right? So when a galaxy is moving away from us, things get stretched. When things are moving towards us, they get squashed. It's kind of like it's pushing it in front of it or it's dragging it out behind it. This means things would be blue shifted. So galaxies would start looking bluer and bluer. Initially, this wouldn't be noticeable to our naked eye, but then it would be. So if the universe were contracting, at some point you'd look up and you would see things rushing towards you. You'd see things getting bluer and bluer in the night sky, which would be really cool. The first thing that would happen to us directly would be Milky Way and Andromeda will collide, which they're going to do anyway. It would just accelerate the process. And then depending how fast this contraction is, at some point gravity is going to take over, right? And the more mass you have, there's going to kind of have this accelerating effect where once it starts collapsing, the collapse is going to accelerate. What would that mean for your everyday life? I mean, it probably wouldn't happen in the span of a year or two. It's like a very, very long process. Things would gradually get bluer in the night sky. Eventually, everything would look kind of different because even sunlight would get shifted slightly. And then stuff would start crashing together, which is very fun. There was an episode of Red Dwarf where they did this, the contracting universe, and somehow they had time going backwards. And I remember I watched this as a kid, and I was really perturbed by this. Like, why would time go backwards in a contracting universe? It wouldn't. It wouldn't. I'm still annoyed that they did this because it really confused me. But it is not true. Time would not go backwards. So, because otherwise time would be accelerating today, and it's not. Anyway, don't trust your sci-fi for random facts about the universe. Trust me instead. Also fact check me, but yes. So if the universe was contracting, there wouldn't be a noticeable effect on your everyday life. Astronomers would be a bit upset because everything would look weird in the night sky, but it would take quite a few billion years before things would start crashing down on top of you. Okay, gonna catch up with comments here and then carry on. Would be an awesome and terrifying way to go. I guess you're referring there to things crashing on top of us. Yeah, as a kid, yeah. I'm trying to think when I watched Red Dwarf, and I feel like I was in my teens when I watched that. Yeah. Age is catching up to all of us eventually. I realized recently that by the time LISA launches, I'll almost be 50. Yeah, anyway, fun times, fun times. Let's go back to the questions there before existential doom sets in again. Okay, if the universe was contracting, we read that one. If dark energy is based on the size of the universe, increasing with size, then the early universe would be too small for dark energy to cause inflation. Exactly. That's very well put there, Paul. That's exactly what I was trying to get at there. And yeah, it's to do with the way it's not really that the dark energy is based on the size of the universe. It's just the way it dilutes with the scale factor, which gives you an idea of the age of the universe, and you can use the scale factor to calculate the size of the universe because it's all connected. But yes, it's more based on the way things dilute throughout the universe. If you knew dark matter was fake, would you tell us? Absolutely. I definitely would tell you. Yeah, I was definitely a teenager when I watched Red Dwarf. Thank you for confirming that. And yes, and nothing wrong with being 50. No, but like 50s. If I'm in my 50s by the time LISA launches, like by the time we get data and process it, there's like I'll retire not long after LISA does its stuff. I mean, obviously not, but it will still be 10 years and so on. But still, it's just like career-wise, I feel like that's a long way away from me. By that point, hopefully I'll be a tenured professor, but who knows? Okay, so if dark matter was fake, would I tell you? Absolutely. Science is amazing, and science is a continuous process of updating our knowledge based on new facts. If dark matter is not real, this is the biggest shakeup in cosmology in the last 30, 40, 50 years. This would be an amazing point. This is when people can come forward and say, okay, back to the drawing board, let's do this again. We don't know what's happening. We have not been able to find anything that could explain all of the observations in our universe as accurately as dark matter can. If there's no dark matter, we need to ask ourselves, why does this cosmic microwave background radiation look the way it does? It's taken all of 22 minutes today. If there's no dark matter, there's so much we don't understand. And that would be so fun and so amazing. I like it when our theories are correct, but it's even more fun when we find something unexpected. A couple of us were talking the other day about the nanograv result, the very amazing, cool thing that I was talking about the last two streams of pulsar timing array, little pulsars, rapidly rotating neutron stars with light beams that have been used to measure gravitational waves. And it's really cool. But they found what they expected to find, which is amazing, and I don't want to downplay it. But we were saying, like, wouldn't it have been more fun if they'd found something unexpected, right? If what we expected wasn't there. So if I knew dark matter was fake, there is no way I would be keeping this a secret. I would be shouting about this because it would be an exciting time. Like, I've spent all of my career, or like 15 years of my career working on dark matter mainly. If dark matter is suddenly not there, yeah, it means all my work has been wrong. But that's fun, that's exciting, that's interesting. And I think a lot of scientists share this opinion. This is not some mass conspiracy where we're trying to sell you dark matter. We don't get money out of this, really, not much. Like, scientists do not get paid much. There's not this mass conspiracy of like big dark matter. It's just like, what would we gain from lying to you when there's a whole new thing to investigate? So yeah, if I knew dark matter was fake, I would try to keep it secret up until the press release, and then I would absolutely be shouting about it. Currently, we don't have any reason to think dark matter is wrong, but maybe the models of dark matter we've been looking at are not the right ones. But yeah, if I knew dark matter was fake, I would absolutely tell you, if I was sure. If it's just me saying, I've decided that dark matter is not a thing, maybe don't believe me, wait for peer review, other scientists to weigh in on this and agree. So yeah, maybe don't listen to just one person saying this. But yes, if dark matter were fake, I would absolutely tell you. This would be so fun. It would be so interesting. That is predictably too hot to drink. I know that it's still too hot to drink because that cup retains heat too much. Yeah, I'm a corporate shell for big science. I'm trying to convince you to invest in science so that we can do more science. That's our end game. What's the big science agenda? To do more science. It's like, what's the gay agenda? Be gay, do crime, have fun. It's like, what's the big science agenda? Do science, have fun. Maybe don't do crime, but do science. Yes, I'm a corporate shill for big science. Absolutely. God, I hope YouTube doesn't choose that as one of the chapter headings. Okay, back to the questions. We did dark energy, we did dark matter. Did you ever, question from Scott here, did you ever talk about the hypothetical black hole stars that may have existed during the early universe and may be the cause of supermassive black holes? Okay, so there are black holes. Black holes are a fun topic. Let me just check the questions and then carry on with black holes, just making sure I didn't miss any relevant comments there. You miss how many random people would watch during the Periscope days? Yeah, honestly, me too. Yeah. Periscope was fun, but Periscope was short-lived attention span. People would come in for like 30 seconds and move on. Whereas some of the people here have been following me for almost 8 years now, coming in every single week and engaging. And that's much nicer than people who come in for 30 seconds, make problematic comments and run away. Periscope was great for a lot of things, but the amount of trolls I got on the Periscope streams was very perturbing, and the amount of comments I got off screen from people on Periscope, yeah, you people do not want to know the amount of comments and stuff that I got for that. So YouTube is surprisingly much nicer than Periscope. Okay, so there was this fun question, black holes. Black holes are regions of space-time that are so dense that nothing can escape, not even light. You would have to travel faster than light in a vacuum in order to escape the gravitational pull of a black hole. As far as we know, nothing can travel faster than light in a vacuum, and therefore nothing can escape a black hole. How do you make a black hole? There's several different ways. Basically, what you need to do is you need a region with an incredible amount of density. The most common way to do this is you take a star. The star reaches the end of its lifetime. The star expands because it is producing a lot of gas. A star is a constant battle between gravity pulling things inwards and pressure pushing things outwards. And you have this equilibrium. When a star reaches the end of its lifetime, this equilibrium breaks. At some point, it will start expanding gradually, then it contracts. And because the way it contracts, gravity pulls everything down. And at some point, the core is going to collapse into a black hole. Once this happens, the gravity is concentrated there, and everything else is thrown outwards in a massive supernova explosion. And then you have this remnants, this leftover, which is going to be either a black hole or a neutron star or a white dwarf, depending on how massive it was. These black holes can then smash together and grow bigger. They smash together, they get bigger, blah, blah, blah. You end up with big black holes. But we know that at the center of every galaxy, there is a supermassive black hole. Black holes that are billions and billions and billions of times the mass of the sun. We don't really know how black holes got so big. And if you only look at stellar black holes, these black holes that are formed when stars collapse, it gets quite hard to think about how did supermassive black holes come about. Then there's this idea that in the early universe, you could form black holes without going through the star formation state. Depending on how inflation happened, for an example, you could have regions of space-time that are so dense that they can automatically collapse into a black hole. These black holes, hypothetical black holes known as primordial black holes, would have been around for a much longer time, which would have given them much longer to grow and could potentially be the seeds of the supermassive black holes in the center of galaxies. I did do a stream just about this topic. It was in the HAPS days, and I had Sophia Nazar join me, and we talked about supermassive black holes and dark matter. It was really cool. I'm not sure if that one's on YouTube. That was in the HAPS days, and I'm not sure if I uploaded that one. I will check. If not, I can upload it because I have all the HAPS ones saved, so I can just upload it if I didn't already. Then there's another idea of maybe when galaxies started to form, you could have something like a quasar, which is like a huge energy burst at the center of a galaxy. And maybe you could have had something like a galactic-sized black hole just collapse at the center of a galaxy. And that would set the seed for the supermassive black hole. So it's a kind of a chicken and an egg question, like what came first, the supermassive black holes or the galaxies? We're not completely sure. So there's a shortish version of that. Supermassive black holes, we don't know where they came from. Could have been primordial black holes, could have been massive galaxies just collapsing into a black hole, could have been a lot of things. We're still trying to figure that one out. Okay, let me just check comments, then go back through the questions. I will never cave into peer review pressure. I mean, I should. That's literally how science works. So yes, we should do that. Yes, definitely should do that. Supermassive black holes just means very massive. It's not suggesting some qualitative difference from normal massive black holes. No, the only difference here is the mass. Like a normal black hole, I do the quotation mark or the bunny rabbit ears here because normal black holes are still amazing objects, but they're like 5 times the mass of the sun, 30 times the mass of the sun, 100 times the mass of the sun. Supermassive black holes are billions of times the mass of the sun. I think the biggest one is like 60 billion times the mass of the sun. And that's a lot. We often have a problem conceptualizing what a billion actually is. And this is why we're okay with billionaires when billionaires just should not exist in society. It's because we can't conceptualize how much bigger a billion is than a million. Capitalism rants aside, it's twice today. Yeah, so a supermassive black hole is like billions of suns. You take the sun 60 billion times. That's a ridiculous amount of stars that you're putting together there. So yeah, supermassive black holes are incredibly big objects. They are ridiculously big, and just thinking about the size of them is ridiculous. So when we say supermassive black holes, they're not physically much different than a normal black hole. They're just orders of magnitude bigger, and so big that we can't even think about just how massive these things are. Okay, back to questions. There were some very good questions here. I saw a question from Mito. If there is a galaxy made of antimatter, can we detect it? Does it emit electromagnetic radiation at the same wavelength as normal galaxy? Excellent question. So every particle in the universe has a hypothetical antiparticle, which is a particle that has different quantum properties. So for an example, an electron, which has negative charge, has an anti-electron partner, which we call the positron, which has positive charge. If an electron and a positron come together, they annihilate and they produce radiation, particles of light, photons. We know that in the early universe, we had antimatter and matter, but there was a bit more matter than antimatter. For every 1 billion particles of antimatter, we had 1,000,000,001 particles of normal matter, which is good. Because as the universe cooled down, these particles could come together, particle, antiparticle, annihilate. If they had been produced in equal parts, the whole universe today would just be radiation. There would be no matter. We would not be here having this conversation. But fortunately, there was this slight imbalance. So there was a bit more matter than antimatter, which we don't know why, but we're glad it happened. This means that having structures made of antimatter is very difficult in the universe today because most of the antimatter was annihilated. Any antimatter that we find today is created today. And as soon as it finds its corresponding matter twin, it gets annihilated, right? So we can produce antiprotons in small quantities, and as soon as they meet a proton, they annihilate. We can produce anti-electrons, and as soon as they meet an electron, they annihilate. So we think it will be quite difficult to have a universe made of antimatter, or have a galaxy, made of antimatter, because it would need to exist in a complete vacuum away from everything else. So does it emit electromagnetic radiation? If it annihilates, like if you did have antimatter, when it meets its matter counterpart, it annihilates and produces electromagnetic radiation. The wavelength in our universe, we've been able to see things at many different wavelengths, ranging from gamma ray, which is high energy, to microwave, which is low energy at the other side. So we can see things across the electromagnetic spectrum. Antimatter galaxies, we would be able to see if they annihilated, but we don't think there's any way they could exist because they already would have annihilated. So we don't think there are galaxies made of antimatter. And if there were, we would probably detect them when they meet normal matter and annihilate. Then, of course, you can ask, like, are there antiphotons, which would be a great question to ask. And the answer is probably no, because of the quantum physics that we know about particles, about photons, no antiparticles there. So there's no anti-light. Then you can ask a cool question of, is there dark light, like in the dark matter sector? And that's a harder one to answer. But yes, if there were a galaxy made of antimatter, we don't think that's a possibility, but we would probably detect it as soon as it annihilates with a normal galaxy. Okay, back to the questions. And again, I'm not saying there's anything wrong with 50s, just me being in my 50s when LISA launches seems like a really long time away, and I want LISA to launch now, not so many years into the future. Okay, let me just check comments and go back through the questions, because we have a lot of questions today and a lot of comments. I think there's a good number of stellar mass black holes. There then nothing for a good while, then it jumps to the supermassive black holes, and they're trying to figure out why. Yeah, there's this big gap in the middle, and we're like, we have small black holes, we have supermassive black holes. Why don't we have black holes that are 1,000 times the mass of the sun? Good question. Okay, is there an upper limit for the mass of a black hole? Excellent question as well. So I know there's a bunch of questions I've missed in the meantime, but sticking on the topic of black holes before I go off on another tangent. There are different limits on the mass of black holes. For an example, the ones that form with stars, we think there's an upper limit based on at the point when they form, because at that point you're limited by there's a balance between the pressure coming in, gravity coming in, pressure going out. When you reach that balance, you're going to switch over into supernova. And depending on the mass of the star, you either end up with black hole, white dwarf, or a neutron star. Okay, so at that point, you have a limit on the mass of the black hole when it forms. But then black holes can grow by having other matter fall on top of them. As they continue to grow, there's no limit. So we've been able to see black holes of a lot of different masses. The upper limit that you have there is based on the mass at the time it was formed and how long it's had to grow, and that gives you an upper limit. And that's why we think there's a jump between stellar mass black hole masses and then suddenly the supermassive black holes. So they're based on what we know about the age of the universe, when stars have been around, that gives you the upper limit. I can't remember the numbers, but that's where the upper limit might come from. And then to jump to supermassive black holes, that's the big problem. 1 million seconds is 11 days, 1 billion seconds is 31 years. So yes, that is a nice comparison in order to see the difference between like millions and billions. Yeah, 1 million seconds is 11 days, 1 billion is 31 years. There's a lot of these comparisons online, but I think this is something that we don't visualize. It's very difficult to visualize orders of magnitude. Why do particles and antiparticles annihilate? Just having opposite electric charges isn't enough. Yeah, opposite quantum numbers. So they have opposite charge and opposite a few other things. And when they come together, they annihilate. It's something that they do. We know that part of these opposite quantum numbers is enough to cause them to annihilate and produce radiation. And that's how we get most of the light we see today. Even the light the light that's here in the cosmic microwave background radiation, this comes from particles and antiparticles annihilating in the early universe. So the upper limit is based on the age of the universe, and there's the problem: the universe isn't old enough to explain supermassive black holes. Exactly what I was saying. Back to the questions. There's a bunch of really, really cool questions that I know I still want to answer. Okay, so we did the galaxy made of antimatter. What do you think? Question from Ben here. What do you think of physicist Lucas Lumbray's theory that the universe isn't expanding but is flat and static? Expansion is instead explained by the evolution of the masses of particles over time. I think there's not enough scientific evidence to support this hypothesis. I wouldn't call it a theory because it has no evidence to support it. It's an interesting perspective. It's interesting to consider, but it doesn't match the observations. You know, we're pretty sure that the universe is expanding. Why would particles' mass evolve over time? We don't have any reason to believe that they do. And if they did, it wouldn't. How would that mimic an expanding universe? Yeah, I don't share that view, and I don't think it's a prevalent view within the scientific community. But there are always people challenging the status quo, and that is a good thing because people need to propose these ideas and think out of the box. The problem is your idea needs to work, and if it doesn't fit the data, it doesn't fit the data. Okay, I see there's the excellent question here. Does the Higgs boson have an antiparticle? And this is a really, really good question. And it touches on something that I just kind of brushed over when I said that photons don't have particles. And I'm just looking for an image here, which is my standard model of particle physics. Or not mine, but the existing one. My changing slides is a bit slow, and I need to get to image like 50 out of a lot, and I'm on 3. So it's just going to take a minute. So bear with me here while I look for the standard model of particle physics. I really hope I have it here and it's not just disappeared. Okay, so standard model of particle physics. These are the particles that make up normal matter in the universe. These are the building blocks of normal matter. And here you can see we have 3 main categories. We have quarks in purple at the top left, leptons in green, bottom left, and then we have the gauge bosons on the right in red, and the Higgs boson yellow on the red, on the right side, kind of not fitting in with things. Okay, the quarks and the leptons are what we call fermions. Now, the fermions are kind of like the Lego bricks that you're allowed to use. Imagine I give you 12 different Lego bricks, a bunch of ups, chimes, tops, down, strange bottom, bunch of a bunch of leptons as well, and say, these are all the pieces you have. Now build me a universe. Well, you won't build a universe, build me the normal matter in the universe. But the way you're allowed to put these pieces together, the instructions are given by the bosons. So you have the fermions, which are the building blocks, and you have the bosons, which is the ones that tell you how the blocks can go together. Whether they have 4 prongs that go into 4 or 3 that go into 3, that's given by the gauge bosons. So we have this different category here. We have the fermions, which are made up of quarks and leptons. The main difference here being that quarks can't exist by themselves. They're always bound together with other quarks, while leptons can exist by themselves. Every quark and lepton has an antiparticle. For every up, you can have an anti-up. For every chime, you can have an anti-chime. You can have anti-electron, anti-mu, and anti-tau. Let's leave neutrinos out of this conversation. Neutrinos at the bottom row here are a bit confusing and messy, and let's not talk about neutrino antiparticles. But yeah, the supersymmetry particles are missing from this model because we have not found any evidence for supersymmetry, unfortunately, so it's not part of the standard model of particle physics, or fortunately, depending on your perspective. So you have fermions, you have quarks, you have leptons, and then you have bosons. Now, the fermions can have antiparticles. If we go back to this thing that I was saying here about the charge, you can see each one of these things has 3 numbers. I hope you can see it. So you'll see there's 3 numbers. The top one is the mass, the second one is the charge, and the third one is the spin. So the charge and the spin are quantum numbers. And you can see, for an example, the electron has charge -1, muon has charge -1, the downs and the strange have charge -1/3, and the ups and the chimes have have charge 2/3, which is also when you group them together, then you get normal numbers. But then if you look at the bosons, you'll see that they actually have charge 0. So bosons don't have antiparticles. We think that the antiparticles are for the fermions and not for the bosons. Higgs doesn't have charge, so Higgs doesn't have an antiparticle. Then you can ask questions of, okay, but could you still have an anti-Higgs? Is there a way to make that happen? Some people are working on models where you could have a Higgs anti-Higgs. But in general, because charge is 0, how do you have something with opposite charge when charge is 0? Right, this is also what I said before, that a photon doesn't have an antiparticle because it has charge 0. So the particles that have charge 0 don't have an antiparticle. So the Higgs boson does not have an antiparticle, but the fermions do. So this is all to the best of our knowledge, of course, based on all of our theories and models. Someday we might be proven wrong, but we don't think that particles that have 0 charge can have an antiparticle. So to answer the very, very good question there, Higgs particles should not have antiparticles. Is there some kind of logic behind names like top, bottom, and strange, or is it random? So up and down were the first ones that were found, and they were named based on preference, like up, down, a bit of mass difference there. Then charge, chime, and strange came along, the names there. I think there was a historical reason for the names, but I can't remember it. And then we had, I've just realized I can change my slides in a different way. Sorry, I just found another button on my screen here. That's a new feature in Restream. How very cool. Okay, I've got a cool new series of buttons in Restream. Just got very distracted. I'm like the weather person, the weather guy who suddenly saw his screen could move. I just found buttons. Sorry, tangent there. Yeah, so up, down, chime, strange. Those had historical reasons. Top and bottom were initially named truth and beauty. And at some point, people decided this was weird and they changed it to top and bottom. So now we have those 6. I don't know if there's any other historical reason for it other than just that's the name they were given. And then you have all the other ones. So very good question. We don't think the Higgs boson has an antiparticle because it's a boson, and bosons don't usually have antiparticles. Press all the buttons, right? When there's new buttons, you have to press buttons. Now, a few people at work have been joking about the fact that if I see a button, I want to press it. If I see a big red button that must never ever be pressed, I want to press that button. I love pressing buttons. I went to a science museum recently that I feel like it knew me on a deep level. It knew what I needed. because there was a big screen with a lot of dials you could turn, and then the big red button with a sign saying press here. And I was like, haha, I've got a button I can press. And if you press that button, there was a loud explosion noise and the whole floor shook. It was so much fun. It's like, here's a button I'm allowed to press. And I pressed that button so many times and I was giggling every time. Yes, anyway, press all the buttons. That's how we do science. We just mess about and press buttons and see what happens. Yeah, antiphotons just have charge of -0. And when we figure out what -0 is, we can go from there. But yeah, press all the buttons. If I find new buttons, I've got to press them. Absolutely. Do not trust me with a button that says do not press. I will press it. Billionaires are like the supermassive black holes of the economy. They're unfathomable and there's no reason they shouldn't exist. Right? Unfortunately, billionaires have a conscience and they could just choose to not be billionaires. And supermassive black holes actually serve a purpose. They keep galaxies together. So supermassive black holes are good and don't deserve to be compared to billionaires. Billionaires, on the other hand, should absolutely be thrown into a supermassive black hole. What about the electrocute yourself button? There's a famous experiment about this. Yes. You know, if I get a button and I press it once and I electrocute myself, as long as it doesn't, kill me or give me serious problems, I would want to know, is that a one-time thing or is that going to happen every time I press this button? I would absolutely press it a second time. Maybe not a third, but you need to know if is it a fluke or this. Do not trust me around random buttons. I should not be trusted with them. Yeah, we were at a place recently, City Hall in like at a conference. There was a City Hall and there was like an event at the City Hall. They always like giving us fancy things like that, and we got a speech from the deputy mayor, usual stuff. And then we were left to wander in this City Hall, and one room had big red buttons on the wall, and I was like, I want to press them, and my colleague said no. I was like, well, there's no sign telling me not to, so I pressed the buttons, and it was just a light switch. It was very disappointing, but it was fun that I got to press the random buttons. Anyway, let's see. Supermassive just means very massive. We went through that one. Going back through the comments here, I think there's a good number of stellar mass black holes. Yep, we covered that one. More questions. Okay, very interesting question from James here. Our expanding universe may just be being pulled into a larger parallel universe that is contracting. So that is an interesting thing, and people are looking into this. People have looked into this. But the idea of if parallel universes or the multiverse exist, we have no way of knowing about it because we are limited to the information contained within our own universe. If there are a billion other multiverses out there, we will never be able to communicate with them. By definition, we only have access to the information in our own universe. So hypothetically, if there is another expanding universe or another universe close to ours that is contracting and we're being pulled in, it would seem weird because how would the gravitational force of a separate universe be affecting us? But you can even look for this because there's a famous spot on the CMB, cosmic microwave background radiation. If you look kind of like right down here, just imagine right where my finger is right now, like bottom right-hand part of the image, there's these really blue spots. And this is an anomaly. It's a lot more blue than we expect and it's a lot bigger than we expect. This is known as the cold spot on the CMB. And there's a lot of research into this. Is this just statistical fluke or is there some deeper meaning? And one idea was, could this be the imprint of a parallel universe that bumped into ours at some point? Unfortunately, it doesn't, or fortunately, again, depends on your perspective, it doesn't look like that's compatible with the data, but it is something that people are looking into. So even though we have no access to other universes and we don't think that we're being pulled into a contracting parallel universe, there you can still come up with fun ideas of how could we even test these scenarios, and people are looking for ways that you could test these things that sound like they shouldn't be able to be tested. But if there is a parallel universe that is contracting and pulling us in, it would be quite hard to test and prove, and we don't have any reason to suspect that is the case. Okay, going through questions again, I think I'm almost caught up. And then there's a bunch of new questions that keep coming up. I love all the questions today. Lots of cool questions. Top and bottom is not weird at all. No, not at all. I don't know what you mean. I'm not going to comment further on that. Okay, more questions. How many electric shocks would confirm that it's consistent? If there's a button that electrocutes me, I think if I press it once, get electrocuted, it's like, okay, might be a fluke. If I press it a second time, I probably would stop at 2 at that point. Like, okay, maybe let someone else press it if they want to. But I think I would stop. I would stop at 2. Okay. The Milgram experiment dealt with whether or not people are willing to harm other people if an authority figure told them to do. Yeah, yeah. I'm not going to go there. Not going to go there. Don't think I'm qualified to answer that question. Back to fun questions. Question from David Howden here. If neutrinos are their own antiparticle, which I think you said was one theory, why don't they just annihilate themselves straight away? Excellent question. Very excellent question. The thing is, you need the neutrinos, you need a neutrino and an anti-neutrino to annihilate. If neutrinos are their own antiparticle, you need a neutrino and a second neutrino. Neutrinos move almost at the speed of light. They're very, very, very quick. So getting neutrinos like close enough to actually annihilate becomes a bit harder, because then you need them to be kind of in the same space with the right interaction to annihilate. Now, often, like with electron and positron, you have the advantage that you have the electromagnetic interaction, which is kind of strong. Neutrinos don't interact via the electromagnetic force. They only interact via the weak force and gravity. And the weak force is very, 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 very weak, as the name implies. Still stronger than gravity, but weak force. So then it's quite hard, once you have particles going out doing their thing, to get this interaction. So if neutrinos are their own antiparticle, indeed two neutrinos of the same flavor could annihilate. But first you need to have all your neutrinos together to make this happen. So it's something that statistically is a bit harder to realize, but it could happen. Can you explain the Eddington limit? It somehow limits how large star can get. Yeah, so there's two limits that I always mix up in astronomy, and the Eddington is one of them. So there's the Eddington one and the other one. So when, as I mentioned before, a star is a constant battle of pressure and gravity, like pressure pushing things outwards, gravity pulling things inwards. And this actually gives you a balance, a limit. The stars can't grow more than a certain amount, because then they would be too big and they would collapse under their own mass. So the Eddington limit is basically the radius at which you reach this balance between pressure and gravitational force. And if it looks like I'm just reading this, it's because I just Googled it to confirm that the Eddington one was the one I had in mind and not the other one. Then that also gives you the Eddington luminosity, which is kind of like the maximum luminosity a star can have when it reaches this mass, because you can relate the mass of the star to its brightness or luminosity. So yeah, the Eddington limit is just this balance between pressure going outwards and gravity going inwards. The Eddington limit is the point when you're at that limit. When a star reaches the end of its lifetime and collapses, it kind of breaks that threshold. It goes one way or the other. Usually it collapses into a black hole, it explodes as a supernova. You often get both, but that's because it's kind of broken the Eddington limit. But the Eddington limit is this balance between pressure going out, and gravity going in. So yes, then you can do a lot of fun things like calculate how bright stars can be hypothetically based on this, or theoretically based on this. It's very cool. Okay, going through the comments, I feel like I'm caught up with a lot of these now. The local buses have a big red button on the windows to break the glass in an emergency. Yeah. There's an image that goes around on the internet periodically of like a big, huge thing that you can press, and there's just a label attached saying "don't." It's like, but you could, yeah. It's like the Doctor Who episode, the first one where we get David Tennant, and there's this big red button, and Tennant is like, if I see a big red button that must never ever be pressed, I'm going to press it, and then he presses it. Yeah, do not trust me around buttons that I literally cannot press. Okay. Ignoring all the questions off topic there. The electric button experiment sounds like a cow mooing in a museum with only one witness. Yes. How many times do you need to confirm? So context here. Me and my mother Ange went to a museum last year, and I heard a cow mooing. I was alone in hearing it. I am convinced to this day that the cow was mooing. Also, that museum was the creepiest museum I've ever been in, so I'm not going back to confirm if the cow was mooing. But there was no button to press to make the cow move, so I'm just going to assume that cow was moving. Eddington limit also applies to maximum star size. Yes, you get the radius and the mass because these two are often connected with stars. So then you get the upper thing there. I think I might actually be caught up with all of the comments. So if there's a question that I missed, please feel free to ask again. I think I got through all of the questions or comments. It was a ghost cow. No, the thing is, it was a figure of a cow. Like if you stuck your head through a wall, there was a figure of a cow. And I'm sure it had a motion sensor, and depending where you were, the cow would move. Because there were also random sound effects in this museum, like a creepy child laughing. I'm just assuming that was a sound effect. But this cow, the motion sensor only worked for me somehow. So yeah, it was a ghost cow. The whole museum was just very, very, very creepy. But the ghost cow was the least creepy part of the entire museum somehow. The murder room was fun. Anyway, I think I've caught up with all the questions. If not, please do feel free to ask again. It's always easy for me to overlook questions, but you all had a lot of really fun and cool questions today, and it's always interesting and exciting. I like talking about all these random questions. So yeah, if you have any questions, you still have me for 3.5 minutes, so you can still get in your last minute questions. And I have no idea what I'm doing the next few weeks because I have way too much stuff going on. So let me just recheck if there will indeed be a stream next week. Next week is Sunday, 23rd. There should indeed be a Cup of Cosmology next week, Sunday, 23rd. Then the week after, there is a Finnish thing happening that I may or may not be going to on the Sunday, but if I don't do the stream on the Sunday, it would be on the Saturday. Yeah, I should be doing streams the next 3 weekends. The next 3 weekends, I should be online, barring some random thing happening. There should be a Cup of Cosmology the next 3 weekends. And then I'll be back on traveling again, so then it's going to get a bit messy, crazy again. We'll see, but at least for the next 3 weeks, there should be a Cup of Cosmology. Have we discovered any exoplanets with exomoons? The problem with exoplanets are planets outside of our solar system. Exomoons should be a moon orbiting a planet outside our solar system. The problem is these are very, very hard to detect. Right, already finding exoplanets is very difficult. The way we usually do this, or the most common method, is the transit method, where you look at a distant star, you look if the amount of light you're receiving from this star dims slightly, and if the light you receive from the star dims slightly, like every few days, by the same amount, then you can say there's something passing in front of this planet every few days that is dimming the light by this amount. You can also do a motion thing where you look at because any planet will have a slight pull on the star that it's orbiting around as well. So then you have the slight wobbling of the star based on the planet. So using that, you can also try to look for these exoplanets. But then to have the resolution to peel apart a planet and a moon far off in a different solar system, we don't have that resolution yet. And just to put it in perspective, until 20 years ago or so, we didn't realize that Pluto had a massive moon. We thought Pluto was a fully fledged planet. And then at some point, we got the resolution to see actually Pluto is a lot smaller than we thought. And there's a second blob there, which is its moon. And that's why Pluto got demoted as a planet, which is a great piece of evidence of how the scientific method works. We get new data, we adapt our theories. Pluto deserves to be demoted. Pluto got promoted. Pluto deserves to be demoted as a planet because that's how science works. And yeah, we demoted the planet named after the god of death. What could possibly go wrong? The world's been perfectly fine ever since then. So my point there was a point to that. The point there is that it took a long time for us to have the resolution to be able to see in our own solar system that Pluto had a moon. So trying to see this for planets light years away in different solar systems or different stellar systems is really, really, really difficult. Charon was discovered in 1978. Wow. Was it really 50 years ago or like 45 years ago? Wow. I always think of that as like 20 years ago, but yeah, the 80s were indeed 40 something years ago, as I was reminded a few days ago. So yes, okay, but still, it took us ages to have the resolution to be able to tell apart Pluto and Charon. So now to do that in another system far off is just really difficult. So we found thousands of exoplanets by now. We found systems that have multiple exoplanets, but having the resolution to find moons, like exomoons on exoplanets, is asking us to do a lot. People are working on it. It would be very cool. Also, it seems like having moons is the usual thing. If you look at our solar system, practically everything has at least one moon. So not having moon seems to be the exception here. So it's quite likely that there are exomoons out there. We haven't found any yet, to my knowledge. I might be wrong about this, but I don't think we've found any just because it's very hard to actually get that resolution. But I think that is a very cool question. It would be fun to think about exoplanets, exomoons, and all the possible systems out there and all the possible life forms out there. The alternate universe bumping into ours is quite interesting. I will always be looking at the CMB differently now. Yeah, it's like this tiny little blue spot, and people are like, is that a sign that another universe bumped into ours? And they have several papers on this. It's a very cool idea. Okay, now we're at the 1 hour mark. I'm surprised my voice lasted so long. I just have a usual cough. It happens a lot when there's weather changes, nothing to be concerned about. And I have tea to help with my voice. But this has been great fun. We've had some really, really fun topics, fun questions, fun directions and tangents that I wasn't expecting to go down, but were really fun. And I love the days when I come on without a topic. Like, let's see what we're going to talk about today. And you all hit me with amazing questions. I mean, we've talked about black holes and antimatter and moons and fun stuff and buttons that should never ever be pressed. No confirmed exomoons, just some candidates. Excellent. Thank you for confirming that, David. Yeah, so this has been super fun. So I should be online again next week. Same time as always. That's 8 p.m. Finnish time, 7 p.m. European time, 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast of the US. As always, there is a time zone converter on cupofcosmology.com if you want to get the next stream in your own time zone. I am also looking at setting up a calendar that people can subscribe to so that then Cup of Cosmology dates, topics, and so on could be like a calendar that you could subscribe to. And that's in the works, but yeah, don't expect that anytime soon. Next week, same time as today, all going to plan. I hope to see you all then. So thank you everyone for the questions. This has been really, really, really fun. Losing my voice, going to go rest now. So thank you everyone for joining. It's been great to have you all here. As always, if you haven't done so yet, do the usual stuff. Subscribe, ring the notification bell, like, comment, usual YouTube stuff, like and subscribe, and go look at Lycan as well because it's cool. Thanks for joining everyone. I hope to see you again next Sunday. And I hope in this... Yeah, can't do my ending properly today. I hope to see you all again next Sunday, and I hope in the meantime you all stay safe and take care of each other.